You're sitting in a dark room right now reading these words, and in the next few seconds you will take a breath. It will feel like nothing. A slight expansion of the chest, cool air through the nostrils, a pause, an exhale. Unremarkable, the most ordinary thing a body does. But in that single inhale, lasting perhaps 3 seconds, moving half a litre of air, you will pull into your lungs roughly 25 sextillion molecules. That is 25 followed by 21 zeros. It is a number so large that if you tried to count those molecules aloud, one per second, you would still be counting trillions of years after the sun has died. Now set that number beside another. The Earth's atmosphere contains an estimated 10 to the 44th power molecules, 44 zeros, an ocean of gas wrapped around the planet extending upward into thinning layers until it dissolves into the vacuum of space. And then consider a third figure, the total number of breaths ever taken by every human who has ever lived. Roughly 100 billion people across 300,000 years of our species' existence, each breathing 12 to 18 times per minute, for an average lifespan that has ranged from 20 years to 80. Add it all together, the breaths of the ancient dead, the medieval living, the industrial masses, the billions alive now, and you arrive at a number vastly smaller than the molecule count in a single inhale. The arithmetic produces a claim that sounds impossible. Every breath you take contains atoms that were once exhaled by Julius Caesar, by Cleopatra, by a child who died of fever in a Roman slum in the year 12, by someone coughing in a hospital room yesterday. The air is not private. It has never been private. It is shared, recycled, intimate in a way that makes the skin prickle. You are breathing right now matter that was inside another person's body, not metaphorically, not poetically, literally. This is not a thought experiment. It is not a metaphor for connection or a parable about the cycles of nature. It is a statistical certainty, confirmed by the scale of molecular mixing and the patient, unavoidable mathematics of diffusion. And it is the strangest true thing about being alive. Let me place you somewhere specific so you can feel the weight of it. Picture yourself standing at night in an empty parking lot, far from streetlights, under a sky dense with stars. The air is still. You take a breath. Half a litre of air enters your mouth, travels down your trachea, branches into the bronchi, and floods into the alveoli, the tiny grape-clustered air sacs at the ends of your lungs. In that breath, 25 sextillion molecules. If every one of those molecules were a grain of sand, you could bury the entire surface of North America under a layer 3 meters deep. If every molecule were a dollar bill, you could pay off the national debt of every country on Earth 1 trillion times over and still have enough left to tile the floor of the Milky Way. That is what you just inhaled, and you will do it again in 4 seconds, and again, 12 breaths per minute, 720 breaths per hour, 17,000 breaths by the time you go to sleep tonight. You will take roughly 25 million breaths this year. By the time you are 30 years old, you will have inhaled more than 300 million times. By 80, closer to 740 million. Breathing is the most repeated physical act of your life, and every single iteration pulls in a number so large it makes galaxies seem countable. Now, the atmosphere, 10 to the 44th molecules, wrapped around a sphere 8,000 miles in diameter, extending upward in layers, troposphere, stratosphere, mesosphere, thermosphere, until pressure fades to nothing and the last stray nitrogen molecule tumbles alone in the dark. The air is not uniform. It is thickest at sea level, where your lungs are designed to work, and it thins exponentially with altitude. Climb a mountain and your body will tell you less oxygen per breath, faster breathing, a faint ache in the chest. Fly to the edge of space and there is almost nothing left. But take the whole atmospheric envelope, from the surf of the Pacific to the top of the ionosphere, and sum every molecule, the nitrogen, the oxygen, the argon, the carbon dioxide, the water vapor, the neon and helium and methane, and you get that number. 10 to the 44th. So here is the ratio. A single breath contains 2.5 times 10 to the 22nd molecules. The atmosphere contains 10 to the 44th. Divide the first by the second and you get a fraction, roughly 1 in 400 sextillion. Your breath is an infinitesimal sliver of the total air, a single drop in an ocean that covers the world. But now consider the other side of the equation. How many breaths have all humans, across all of history, ever taken? Start with the dead. Demographers estimate that roughly 100 billion people have lived and died since anatomically modern humans emerged. Most lived short lives, 20, 30, 40 years. The global average lifespan hovered around 25 for most of human history, rising only in the last 2 centuries. Take a conservative average, 35 years per person, 15 breaths per minute, every minute of every day. That gives you roughly 275 million breaths per lifetime. Multiply by 100 billion people. You arrive at roughly 3 times 10 to the 19 total human breaths across history. 3 times 10 to the 19. Compare that to 2.5 times 10 to the 22 molecules per breath. A single inhale contains more molecules than the sum of every breath ever taken by every human who has ever existed. The disparity is not close. It is not even in the same ballpark. One breath floods your lungs with hundreds of times more molecules than all of humanity has ever exhaled in total. Let that settle. Say it slowly in your head. There are more molecules in the breath you just took than there are breaths in the entire history of our species. The number is so lopsided that it breaks intuition, and that imbalance is what makes the rest of this possible. Because if those exhaled molecules mix, if they do not stay bottled up in one place, if they spread and dilute and circulate through the global atmosphere, then the math becomes unavoidable. If someone exhaled a breath in Rome in the year 44 BCE, and if those molecules are still in the air, and if the air has mixed thoroughly enough, then some of those molecules are in the breath you're taking now. Not many, not a visible cloud, not something you could taste or smell, but statistically certainly at least one, probably several, possibly hundreds. This is the claim that will not go away. Every breath you take contains atoms once exhaled by anyone who ever lived. And the question that follows, the one that seems too strange to be answerable, is whether that claim is true, whether the arithmetic really works, whether the atmosphere is patient enough, chaotic enough, well mixed enough to turn Julius Caesar's final gasp on the floor of the Senate into something you inhale while sitting at your kitchen table 2,068 years later. Before we answer that question, we need to understand what a breath actually is. Not the biological reflex, you already know that part, but the material itself. What is it that leaves your body when you exhale? Picture the moment. You breathe out. A half-liter of air exits through your mouth or nose, warmer than when it entered, carrying moisture, invisible in most conditions but visible on a cold day as a faint fog. What is in that fog? What have you just released into the world? Start with the majority. Nitrogen. Roughly 78% of the air you inhale is nitrogen, a colourless, odourless, inert gas that does almost nothing inside your body. It enters your lungs, sits briefly in the alveoli, and leaves unchanged. You're not built to use it. Plants cannot use it directly either, despite the fact that they need it to build proteins. They rely on bacteria to fix nitrogen from the air into a usable form. Nitrogen is the ghost in every breath. It passes through you untouched, a passenger with no ticket, chemically stable, persistent, cycling through the atmosphere for millions of years. Next, oxygen. 21% of the air you inhale. This is the molecule your body is designed to capture. It crosses from the alveoli into the bloodstream, binds to hemoglobin in red blood cells, and travels through arteries to every tissue. There, in the mitochondria of your cells, it participates in the chemistry of energy production, aerobic respiration, the controlled burn that keeps you alive. Oxygen is consumed. By the time you exhale, the concentration has dropped from 21% to 16 or 17. Your body has taken what it needs. In its place, carbon dioxide. Inhaled air contains about 0.04% CO2. Exhaled air contains 4 to 4.4%, more than 100 times as much. Carbon dioxide is the waste product of metabolism, the byproduct of burning glucose for energy. Your cells produce it constantly. It diffuses from tissues into the bloodstream, travels back to the lungs, crosses into the alveoli, and leaves with your exhale. Every breath out releases roughly 100 times more carbon dioxide than you took in. It is the signature of a living metabolism. It is also chemically reactive, which means it does not stay in the atmosphere as long as nitrogen does. Carbon dioxide is absorbed by plants during photosynthesis, dissolved into oceans, locked into limestone and soil. It cycles. It does not persist unchanged. Then, argon, just under 1% of every breath. An inert noble gas, chemically uninterested in bonding with anything. Like nitrogen, it enters and exits your body untouched. Unlike nitrogen, it is a relic. Most of it was produced by the radioactive decay of potassium-40 in the Earth's crust over billions of years. It accumulates slowly, patient, useless, ever-present. Water vapor, variable depending on temperature and humidity, but typically between 0.4 and 4% of the air. Your lungs add moisture to every breath. The alveoli are coated with a thin layer of fluid, necessary to allow gas diffusion, and some of that moisture evaporates into the exhaled air. On a cold day, that moisture condenses into visible fog. On a warm day, it vanishes into the background humidity. Either way, you're releasing water with every breath. Liquid that was inside your body, now gas, now part of the air, and trace amounts, neon, helium, methane, hydrogen, ozone, ammonia, sulfur dioxide, particulates, dust, pollen, aerosols, microbes, fragments of skin, cloth fibers, smoke if you have been near fire, salt if you have been near the ocean. Air is not empty. It is not a neutral void between people. It is a mobile mixture, a chemical weather system, a suspension of gases and particles in constant motion. When you exhale, you release all of this. The nitrogen and argon pass through you like ghosts, unchanged. The oxygen is partially depleted, swapped for carbon dioxide. The water vapor is added. The trace particles, whatever you inhaled plus whatever your lungs shed, are carried out. This mixture is not sterile. It is not inert. It is matter that was inside your body moments ago, and the moment it leaves your lips, it begins to move. Let us follow a single exhalation. You're standing in a quiet room. You breathe out. Half a litre of air, warmer than the surrounding air, slightly more humid, leaves your mouth. It does not sit still. Warm air is less dense than cool air, so it rises very slightly and spreads as it rises. At the same time, it begins to mix with the ambient air in the room. This process is called diffusion. Molecules of high concentration move toward areas of low concentration until everything is evenly distributed. But diffusion alone is slow, achingly slow. If a room were perfectly still with no air currents, no convection, no drafts, it would take hours for the molecules from your breath to spread evenly throughout the space. The room is not still. Air moves. Even in a sealed room with no windows, no fans, no ventilation, the air circulates. Differences in temperature create convection currents. Your body radiates heat, warming the air around you, causing it to rise. The walls and floor and ceiling have different temperatures. Air slides along those surfaces, creating microdrafts. When you move, you push air in front of you and pull it behind you. A single step is enough to stir the room. Open a window, and the stillness shatters entirely. Outside air, cooler or warmer, drier or wetter, pours in. Pressure differences drive flow. A breeze from one direction pushes air through the room and out the opposite side. Your breath, exhaled seconds ago, is caught in that current and carried away. It moves faster now, meters per second, kilometers per hour. It exits the room. It joins the air outside. Now the breath is in the open. It is no longer a discrete puff. Within seconds, it is shredded by turbulence. Turbulence is not smooth. It is chaotic, recursive, fractal. Large eddies spawning smaller still, down to scales where molecular diffusion finally takes over. A gust of wind catches your breath and tears it apart. The molecules scatter. Some are pushed left, some are pushed right. Some are lifted upward by a rising thermal. Some are pressed downward by a descending air mass. Within minutes, the molecules that left your lungs are distributed across a volume of air hundreds or thousands of cubic meters in size. They are no longer together. They are no longer a breath. They are part of the background concentration, and the mixing continues. Air does not sit still. Atmospheric circulation is relentless. Winds driven by the uneven heating of the Earth's surface, hot at the equator, cool at the poles, create vast convection cells, the Hadley cells, the Ferrel cells, the polar cells. These cells do not turn smoothly. They are disrupted by the rotation of the Earth, by the Coriolis effect, by the topography of mountains and oceans. The result is a global chaos of high-pressure zones and low-pressure zones, fronts and storms, trade winds and westerlies and polar easterlies. Air flows from high pressure to low pressure. It rises where it is warm, sinks where it is cool. It circles, it spirals, it folds back on itself. A molecule exhaled in Washington, D.C. is caught in this flow. It moves with the prevailing westerlies, travelling east at 10 or 20 or 30 kilometers per hour. A day later, it is over the Atlantic. A week later, it has crossed Europe. A month later, it is somewhere over Asia. And it is not alone. The atmosphere is one continuous fluid. There are no walls between countries, no barriers between continents. A molecule exhaled in Beijing will eventually arrive in New York. A molecule exhaled in São Paulo will eventually arrive in Stockholm. The timescale is measured in weeks to months for regional mixing, 1 to 2 years for full global mixing. This is not a guess. Atmospheric scientists have measured it. They have released trace gases, chemically inert, easy to detect, at specific locations and tracked their spread. They have used radioactive isotopes from nuclear tests in the 1950s and 1960s as unintentional tracers, watching how fallout dispersed around the world. The data is consistent. The atmosphere is a well-mixed reservoir. Local inhomogeneities, pockets of pollution, smoke plumes, urban smog, smooth out over time. Within a year or two, the air over the North Pole and the air over the Amazon contain roughly the same concentration of any long-lived gas. The ratios hold, the mixture is stable, and that mixing is what makes the arithmetic work. Because if Julius Caesar exhaled his final breath in Rome in 44 BCE, and if the nitrogen and argon and other stable molecules from that breath are still in the atmosphere, and if 2,000 years is more than enough time for those molecules to mix globally, then some of them, statistically certainly, are in the air you're breathing now. But let's be precise about what that means, because the claim is easily misunderstood, and the misunderstanding matters. You're not breathing Caesar's breath, you're breathing molecules that were once part of a breath Caesar exhaled. The difference is important. A breath is a specific discrete puff of air, a half-litre volume exhaled at a specific moment, with a specific temperature and humidity, containing a specific mix of gases. That puff does not survive intact. It does not float through history like a cloud, waiting for you to inhale it 2 millennia later. It is destroyed within seconds by turbulence and diffusion. The breath as a coherent object ceases to exist almost immediately. What survives are the molecules, and not all of them. Carbon dioxide is absorbed by plants and oceans within decades. Water vapor rains out within days. Oxygen is consumed and replaced in a cycle measured in thousands of years. But nitrogen, the majority of every breath, is chemically stable. It does not react easily. It does not get locked into rocks or soil or biomass on short timescales. It stays in the atmosphere, circulating, mixing, for millions of years. The same is true of argon. These molecules are functionally immortal on human timescales. They are still here. So the question becomes, if you exhaled 25 sextillion molecules, and if those molecules are now mixed uniformly into an atmosphere containing 10 to the 44th molecules, what is the probability that a single breath taken anywhere on Earth will contain at least one of those original molecules? The math is straightforward. The concentration of your original molecules in the global atmosphere is 25 sextillion, divided by 10 to the 44th. That is 2.5 times 10 to the negative 22, a vanishingly small fraction. Now take a single breath. 25 sextillion molecules. Multiply that breath by the concentration. You get roughly 600 molecules from the original exhalation. 600. Not one. Not a few. Hundreds. Statistically, every breath taken anywhere on Earth contains hundreds of molecules from any single well-mixed historical breath. The probability is not just high, it is overwhelming. It approaches certainty. Run the calculation for Julius Caesar. Assume he took his last breath on the Ides of March, 44 BCE, on the floor of the theatre of Pompey in Rome, bleeding from 23 stab wounds. Assume that breath contained the usual 25 sextillion molecules, most of them nitrogen. Those molecules dispersed into the air of Rome. Within days, they were carried by winds across the Mediterranean. Within weeks, they were over Africa and Europe and the Middle East. Within months, they were part of the global atmospheric reservoir. 2,000 years is more than enough time for complete mixing. The descendants of those molecules, if we can even call them descendants since the molecules themselves have not changed, are everywhere now. In the air over the Arctic, in the air over the Sahara, in the air in the room where you're sitting. Take that breath. Statistically, you just inhaled hundreds of nitrogen molecules that were once inside Caesar's lungs. Not because of magic, not because of fate, because of arithmetic, because the number of molecules in a breath is so large, and the volume of the atmosphere is finite, and mixing is thorough, and time is patient. The same calculation applies to anyone who ever lived. Cleopatra, Confucius, a Neanderthal hunter 40,000 years ago, a child who died in the plague, your grandmother, someone who died yesterday in a hospital in Delhi. If enough time has passed for mixing, a year or two, then the molecules they exhaled are in your lungs now. This is not poetry. This is not metaphor. This is the unavoidable consequence of scale and statistics. And once you see it, you cannot unsee it. The air is not private. It has never been private. Every breath you take is a sample drawn from a shared reservoir, and that reservoir has been breathed and rebreathed by every living thing with lungs for as long as lungs have existed. But here is the paradox. If this is true, if the mixing is so thorough, if the numbers are so large, if the claim is statistically certain, then why does it feel impossible? Why does the mind resist it? Because we do not see it. We cannot see it. A molecule is far too small. Even under the most powerful microscopes, individual gas molecules are invisible. You can infer their presence, measure their effects, but you cannot watch them move. And even if you could, there would be no way to mark them, no way to tag a nitrogen molecule exhaled by Caesar and follow it through 2,000 years of atmospheric circulation. The claim is true, but it is invisible. It rests entirely on mathematical inference, and we do not experience air as a fluid. We experience it as emptiness, as the absence of things, not the presence of molecules. When you look across a room, you do not see the air between you and the far wall. When you wave your hand, you do not feel the individual molecules of nitrogen and oxygen sliding past your skin. You feel, at most, a faint resistance, a slight cooling from evaporation. Air is transparent, nearly weightless, forgettable. It is the background against which life happens, not a participant in life. But it is a participant. It is matter. It has mass. The entire atmosphere weighs roughly 5 quadrillion metric tons. It has pressure. At sea level, the air above you presses down with a force of roughly 10 tons per square meter, held in balance by the air pressing up from below. It has viscosity, compressibility, thermal conductivity. It flows. It carries energy. It carries sound. It carries matter, dust, pollen, water, gases, heat, and it carries history. When you breathe, you are pulling in a sample of that history, not a large sample, not a meaningful sample in the sense that you could chemically analyze your breath and determine whose molecules you just inhaled. The dilution is too extreme. The signal is buried under the noise, but the history is there. The arithmetic guarantees it. And that arithmetic is the strangest, most intimate, most unavoidable truth about air. So let us turn to the numbers themselves. Let us walk through them carefully because the strangeness of the claim rests entirely on the scale of those numbers, and the scale is so large that it defeats intuition at every step. Start with Avogadro's constant. It is one of the fundamental constants of chemistry, a bridge between the world we can measure, grams, liters, pressures, and the world we cannot see, the individual atoms and molecules that make up matter. The constant is named for Amedeo Avogadro, an Italian physicist who, in the early 19th century, proposed that equal volumes of gases at the same temperature and pressure contain the same number of molecules, regardless of what those gases are. He never measured that number. He could not have. The tools did not exist. But his insight laid the groundwork, and over the following century, through painstaking experiments involving electrolysis, Brownian motion, and X-ray diffraction, scientists converged on a value. That value is now defined exactly, locked into the International System of Units as of 2019. Avogadro's constant is 6.0224076 times 10 to the 23rd particles per mole. If you're not used to working with such numbers, let me put it differently. 1 mole of anything, 1 mole of water molecules, 1 mole of oxygen molecules, 1 mole of nitrogen molecules, contains approximately 602 sextillion individual particles. That is the number 6 followed by 23 zeros. It is the number of grains of sand you would need to bury every continent on Earth under a layer half a kilometer deep. It is the number of seconds in roughly 20 trillion years, far longer than the universe has existed. And it is the number of molecules in a volume of gas you can hold in your cupped hands. Now consider a single breath. A typical human breath, what respiratory physiologists call tidal volume, the amount of air you inhale and exhale at rest, is about half a litre. That is roughly the volume of a large glass of water, or a small plastic bottle. It does not feel like much, it barely moves your chest. But that half-litre of air, at room temperature and sea level pressure, contains approximately 25 sextillion molecules. Not 600 sextillion, we are not inhaling a full mole with every breath, but 25 sextillion. That is 2.5 times 10 to the 22nd. Write it out. 25,000 molecules in one breath, in the space of a second or two, every time you inhale. Now set that number against the atmosphere. The total number of molecules in Earth's atmosphere, taking into account all the nitrogen, all the oxygen, all the argon, the carbon dioxide, the water vapour, the trace gases, is approximately 10 to the 44th power. That is a 1 followed by 44 zeros. 10,000 billion molecules. It is an unimaginably large number, and yet compare the two. The ratio of molecules in a single breath to molecules in the entire atmosphere is roughly 1 part in 800 sextillion. That sounds impossibly small. It sounds like a breath should be irrelevant, lost in the vastness of the planetary reservoir. But here is where the arithmetic turns, because even though your breath is a tiny fraction of the atmosphere, it is still 25 sextillion molecules. And when you ask the question, how many of those molecules were once in Caesar's lungs, you're not asking whether one molecule made the journey, you're asking how many out of 25 sextillion did, and the answer, once Caesar's breath has had time to mix thoroughly into the global reservoir, is hundreds, perhaps thousands, depending on how thoroughly you account for chemical removal and how you model the mixing. But the central estimate, the one repeated in textbooks and popular science books, is that any given breath you take contains roughly 400 nitrogen molecules that were exhaled by Julius Caesar on the Ides of March in 44 BCE. Let that number settle for a moment. Not one, not a handful, hundreds, in every breath, right now. The calculation is straightforward. Caesar exhaled molecules. Call it one full breath, half a litre, 25 sextillion molecules. Those molecules dispersed into the atmosphere, which contains 10 to the 44th molecules total. If those molecules mixed uniformly, if every molecule Caesar exhaled spread out evenly across the entire planetary atmosphere, then the fraction of Caesar's molecules in any given sample of air is simply the ratio. 25 sextillion divided by 10 to the 44th. That fraction is vanishingly small, but multiply it by the number of molecules in your breath, another 25 sextillion, and you get back to a number near 1. In fact, you get a number larger than 1. You get hundreds. The atmosphere is vast, but your breath is not small, and the result is that the dilution, extreme as it is not enough to erase the signal. Caesar's molecules are everywhere, and because you are sampling so many molecules with every inhale, you are statistically certain to catch some. This is Avogadro's lottery. You're not picking one molecule out of the atmosphere and hoping it is Caesar's. You're picking 25 sextillion molecules, and the question is not whether you win, but how many times you win. The odds of any single molecule in your breath being one of Caesar's are almost zero, 1 in 800 sextillion. But you're not buying one ticket, you're buying 25 sextillion tickets. And with that many chances, even the longest odds collapse into near certainty. The same logic applies to anyone who ever lived. Cleopatra exhaled. Her molecules mixed. They are in your lungs now. Confucius exhaled. His molecules mixed. They are in your lungs now. A Neanderthal woman who died 40,000 years ago. Her molecules mixed, and they are in your lungs now. The numbers do not care about fame. They do not care about history. They apply equally to the anonymous and the celebrated, to the ancient and the recent dead, to anyone who lived long enough ago that their exhalations have had time to circulate through the global reservoir. The atmosphere is a democratic archive. It remembers everyone and it remembers no one. It simply mixes. But notice the condition. The mixing must be thorough. If Caesar's breath stayed in Rome, or drifted slowly across the Mediterranean but never left the northern hemisphere, then the calculation would fail. The claim depends on the atmosphere acting as a planetary blender, stirring its contents until every sample is statistically indistinguishable from every other sample. And that raises the question, does the atmosphere actually do this? How long does it take? How complete is the mixing? And what, if anything, gets left behind? The atmosphere is not still. It is in constant motion, driven by the uneven heating of the Earth's surface. Warm air rises near the equator. Cool air sinks near the poles. That temperature difference, small in absolute terms but persistent, creates pressure gradients, and those gradients drive wind. The wind moves air horizontally, rising and sinking air moves it vertically, and the result is a vast three-dimensional circulation that spans the entire planet. Start with the largest cells. Near the equator, intense sunlight heats the surface, warming the air above it. Warm air is less dense, and it rises, sometimes gently, sometimes violently in towering thunderstorms that punch through the troposphere and briefly touch the stratosphere. As that air rises, it cools and it spreads outward, north and south, at altitudes around 12 to 15 kilometers. Eventually, near 30 degrees latitude north and south, it descends, sinking back toward the surface and flowing back toward the equator along the surface as the trade winds. This is the Hadley circulation, named for George Hadley, an English lawyer and amateur meteorologist who proposed the mechanism in the 18th century. The Hadley cells are the engine of tropical weather. They are why deserts cluster near 30 degrees latitude. Descending air is dry. They are why the equator is stormy and wet. Rising air carries moisture, and they are one of the primary mechanisms by which air from one part of the tropics reaches another. But Hadley cells do not extend to the poles. Poleward of roughly 30 degrees, the circulation fragments into mid-latitude weather systems, cyclones, anticyclones, fronts, and the jet streams. The jet streams are narrow, fast-moving rivers of air in the upper troposphere, typically found near 30 degrees and 60 degrees latitude in each hemisphere. They meander, split, merge, and steer storms, and they are fast. Wind speeds in the core of a jet stream can exceed 200 miles per hour. Air caught in a jet stream can cross an ocean in a matter of days. Between the northern and southern hemispheres, the mixing is slower but still thorough. The Hadley cells in each hemisphere meet near the equator, and while they do not directly exchange much air, each cell mostly recirculates within its own hemisphere. The intertropical convergence zone, where the trade winds from north and south collide, is a region of vigorous vertical mixing. Air rises, crosses into the opposite hemisphere's upper-level flow, and eventually works its way poleward or back toward the surface. Thunderstorms help. They punch through layers, redistribute heat and moisture, and inject surface air into the upper troposphere where it can be swept into the jet stream. Over time, on the order of a year, air molecules from the northern hemisphere find their way into the southern hemisphere, and vice versa. The process is not instantaneous, but it is relentless. Consider what this means. A molecule exhaled in Rome in 44 BCE did not stay in Rome. Within days, it would have been carried by local winds, perhaps out to sea, perhaps northeast into the Balkans, perhaps south across the Mediterranean. Within weeks, it might have been caught in a weather system and transported across Europe. Within months, it could have been drawn into the Hadley circulation or a jet stream and carried halfway around the world. Within a year or two, it would have crossed hemispheres, risen and fallen dozens of times and become part of the well-mixed background. 2,000 years later, there is no distinction. A molecule that began in Caesar's lungs is no more or less likely to be over the Arctic than over the Amazon, over Tokyo than over Nairobi. The atmosphere has shuffled its deck thoroughly. We have historical evidence of how quickly material injected into the atmosphere can become a global signal. On August 27, 1883, the volcanic island of Krakatoa, located in the Sunda Strait between Java and Sumatra, erupted with a force heard 3,000 miles away. The explosion was one of the most violent in recorded history. It destroyed 2/3 of the island, triggered tsunamis that killed tens of thousands, and sent a pressure wave circling the globe multiple times. Barometers as far away as England registered the wave's passage days later. But the most enduring signal was in the air. The eruption injected vast quantities of sulfur dioxide and ash into the stratosphere, the stable layer of atmosphere above the troposphere where weather occurs. In the stratosphere, wind patterns are slower, but they are global. The sulfur dioxide reacted with water vapor to form tiny droplets of sulfuric acid, and those droplets spread. Within weeks, they had encircled the Earth at the latitude of the eruption. Within months, they had reached both poles. For the next several years, sunsets around the world were vividly red and orange, the result of the fine aerosol particles scattering sunlight. Global temperatures dropped by more than 1 degree Celsius, enough to cool summers and disrupt harvests. The aerosols remained aloft for 5 years before finally settling out. Krakatoa demonstrated, in a way no calculation could, that the atmosphere is a single connected system. What enters in one place does not stay there. But here is the limit. The atmosphere is not instantaneously mixed. It is not perfectly mixed. Location matters. Altitude matters. Chemical lifetime matters. A molecule of water vapor exhaled in your breath does not stay in the atmosphere for thousands of years. It condenses, falls as rain, and cycles through oceans, rivers, soil, and living things on a timescale of days to weeks. A molecule of carbon dioxide does not remain a free gas indefinitely. It dissolves in the ocean, is absorbed by plants during photosynthesis, reacts with minerals in rock. The average lifetime of a CO2 molecule in the atmosphere before it is removed by one of these processes is on the order of several years to decades, though the full equilibration of atmospheric carbon with the oceans and biosphere takes centuries. Only the inert gases, nitrogen and argon primarily, can be counted on to remain in the atmosphere for geologically long timescales. Nitrogen, which makes up 78% of the air, is chemically stable under most atmospheric conditions. It does not burn, does not dissolve readily, does not react with much. When you exhale nitrogen, it stays nitrogen, and because it is inert, it mixes and stays mixed. It is the nitrogen from Caesar's breath that you're most likely inhaling now, not the oxygen, not the carbon dioxide, not the water vapor, and even nitrogen does not mix instantly. If you exhale in your living room and someone across the room inhales a second later, they are not getting a uniform sample of the air in the room. They are getting air that was already near them, with only a tiny unmixed contribution from your exhalation. Local air masses can remain distinct for hours, or even days before turbulence and diffusion blend them. When a factory emits a plume of smoke, that plume can be tracked downwind for miles before it disperses into the background. When a forest fire burns, the smoke can travel hundreds of miles as a coherent mass before it thins and vanishes. The atmosphere mixes, but it mixes over time, and the time required depends on the scale. A room mixes in minutes, a city in hours, a continent in days to weeks, the globe in 1 to 2 years for the troposphere, longer for the stratosphere. So the claim about Caesar's breath comes with a condition. The molecules must have had time to mix. For someone who died 2,000 years ago, that condition is trivially satisfied. For someone who died last week, it is not. If your grandfather died in a hospital in Stockholm 3 days ago, the molecules he exhaled are still mostly in Europe. Some have crossed the Atlantic, some have risen into the upper troposphere and been caught in the jet stream, but the global mixing is incomplete. His breath is not yet everywhere. In a year it will be, in 2 years certainly, but not yet. This is not a failure of the arithmetic. It is a recognition that the atmosphere, vast as it is, operates on human timescales when it comes to mixing. The dilution is fast but not instantaneous. The blending is thorough but not immediate. And for very recent exhalations, there is still a geography to air. The breath you take in Beijing is not quite the same as the breath you would take in Buenos Aires at the same moment. The differences are small, trace gases, pollutants, humidity, but they exist. Over time, those differences fade. The atmosphere is patient. It stirs and stirs and stirs until every sample is indistinguishable, until the breath of Caesar and the breath of a child in a Beijing hospital last year are both, equally, part of the air you're breathing now. The planetary blender works. It is slow by the standards of a hurricane. Mixing takes months to years, not hours. But it is fast by the standards of history. 2,000 years is more than enough. 200 years is more than enough. Even 20 years is likely enough for nitrogen molecules to have made the full circuit, to have crossed every ocean, visited every continent, risen to the top of the troposphere and descended again to sea level, multiple times. The atmosphere forgets location. It remembers only chemistry. So the claim stands. Every breath you take contains molecules exhaled by Julius Caesar. Not because those molecules sought you out, not because there is any connection, any thread, any meaning, but because the numbers are large, the mixing is thorough, and the atmosphere does not care about history. It only cares about diffusion and pressure and wind. And those forces, operating blindly over centuries, have ensured that the air in your lungs right now is a sample, a thoroughly randomized, statistically representative sample of every breath ever exhaled by every human who lived long enough ago. Hundreds of molecules per breath, from Caesar, from Cleopatra, from people whose names we do not know and will never know. The lottery has already been won over and over with every inhale, and you did not even have to buy a ticket. You only had to breathe. But if the atmosphere truly remembers every breath, there should be proof somewhere. Not just statistical proof, Not just the arithmetic we have been walking through, but physical proof. A sample you could hold, a measurement you could repeat, air from a time when Caesar was alive, sealed and preserved, waiting to be opened, and there is. Not in a vault, not in a museum, but in ice. Deep in Antarctica, in the coldest, most lifeless place on Earth, scientists have drilled into the past. They have pulled cylinders of ice from depths measured in kilometers, ice that fell as snow when mammoths still walked, when the last ice age had not yet released its grip, when the atmosphere held different proportions of carbon dioxide and methane than it does now, and trapped inside that ice, in bubbles smaller than the head of a pin, is air. Ancient air. Air that has not mixed with the modern atmosphere, that has not circulated through the jet stream or crossed the equator or risen into the stratosphere. Air that was exhaled by the Earth tens of thousands, even hundreds of thousands, of years ago, and then locked away. The Antarctic ice sheet is not a flat static plain. It is a flowing system, a river in extreme slow motion, fed by snowfall that accumulates year after year, century after century, compressing the layers beneath into ice. Near the coast, where the ice moves faster, the layers tilt and fold and eventually carve off into the ocean as icebergs. But in the interior, at the highest, coldest, most remote locations, the ice barely moves. It piles up, layer upon patient layer, building a vertical archive. Each layer is a year, sometimes a season, sometimes, in the coldest regions, a decade compressed into a band no thicker than your hand. The Soviet Union established Vostok Station in 1957 at the southern pole of cold, a location chosen not for convenience but for extremity. The coldest reliably measured natural temperature on Earth was recorded there, -89.2 degrees Celsius, -128.6 Fahrenheit. Cold enough that exhaled breath freezes into crystals before it can disperse. Cold enough that metal becomes brittle, fuel thickens to sludge, and exposed skin can suffer frostbite in under a minute. The station sits atop more than 3.5 kilometers of ice that has accumulated over 400,000 years, possibly longer. Beneath the ice lies a lake, liquid water sealed under pressure and cold, cut off from the surface for at least 15 million years. But the ice itself, and the air trapped within it, is what the scientists came for. The drilling was slow. The cores were extracted in sections, cylinders roughly 10 centimeters in diameter, each segment a meter or two long, marked, logged, and stored in insulated containers at -36 degrees Celsius. The deeper the drill went, the older the ice, and the older the ice, the more compressed the layers became. A meter of ice near the surface might represent a year of snowfall. A meter of ice at 2 kilometers might represent a century. The work required years, decades. Crews rotated in and out. Equipment failed in the cold. Generators caught fire. In April 1982, the station's chief mechanic, Alexei Karpenko, died attempting to save the generator shed from flames, and drilling halted until November. But it resumed. The project was too important. The ice held answers that could be found nowhere else. In 1987, a joint Russian, French, and American team published results in the journal Nature, covering a 160,000-year climate record extracted from the Vostok core. For the first time, scientists could measure atmospheric carbon dioxide concentrations not from models or proxies, but directly from air that had been sealed away when Neanderthals were still alive. The measurements were precise, repeatable, and they told a story. Carbon dioxide levels had oscillated between roughly 180 and 280 parts per million, rising and falling in rhythm with the glacial cycles, the great advance and retreat of ice that shaped the continents. The warmest periods had the highest carbon dioxide, the coldest the lowest. The correlation was undeniable, but Vostok was only one site, and 160,000 years, though vast by human measures, was a fraction of the ice's total memory. Another project, the European Project for Ice Coring in Antarctica, known as EPICA, targeted Dome C, another remote high point on the East Antarctic Plateau. Between 1996 and 2005, they drilled to a depth of over 3,000 meters and recovered a continuous record spanning 800,000 years. 8 glacial cycles. 8 times the Earth cooled into ice ages and then warmed into interglacials, and every transition was written in the air trapped in those tiny bubbles. The bubbles form naturally. Snow falls on the surface, light and full of air. Over time, the weight of new snow compacts the old. The snow becomes firn, a transitional state between snow and ice, a porous, granular material where air can still flow between the grains. But as the firn is buried deeper, the pressure increases and eventually the pores close. The air is trapped. The firn becomes solid ice and the bubbles are sealed. This process, called sintering, typically occurs 50 to 100 meters below the surface. The age of the ice and the age of the air trapped within it are not quite the same. The ice might be 1,000 years old, but the air inside is younger, perhaps by a century or more, because the air continued to mix in the firn layer even as the ice around it was already forming. Scientists account for this. They model the depth and the compression and the temperature, and they calculate the lag. The dates are corrected. The record is precise. To extract the air, researchers melt or crush the ice in controlled environments. The gas is collected, measured with spectrometers and chromatographs, analysed for carbon dioxide, methane, nitrous oxide, oxygen isotopes. The measurements are cross-checked against other cores, other methods. Volcanic eruptions leave ash layers that serve as dating markers. The eruption of Mount Tambora in 1815, for instance, deposited a distinct layer that can be identified in multiple ice cores, synchronizing the timelines. Stable isotope ratios in the ice itself, oxygen 18 versus oxygen 16, record temperature shifts because lighter isotopes evaporate more readily in warm climates, and the ratio shifts accordingly. Dust layers thicken during glacial periods, when the Earth was drier and windier. All of these markers are woven together into a chronology that is, by geological standards, extraordinarily precise. In January 2025, the Beyond Epica project announced the recovery of a core exceeding 2.8 kilometers in length, preserving a continuous climate record of at least 1.2 million years. The ice at the bottom is compressed, thinned by the weight above, and the layers are measured in millimeters. But the air is still there, still sealed, still waiting to tell what the atmosphere held when early humans were just beginning to chip stone into tools, when the climate was shifting in ways that would shape migration, survival, language, everything that came after. The oldest isolated ice samples ever recovered, from a site called Allen Hills in Antarctica, have been dated to roughly 2 million years. Not continuous layers, but fragments, preserved in unusual conditions where ice flow brought ancient material back to the surface. The air in those samples is older than the genus Homo, older than any human breath, but it is still air, still molecules of nitrogen and oxygen and carbon dioxide, measurable, analyzable, real. This is not poetry. This is not a thought experiment. It is physical evidence that the atmosphere keeps records. That air, invisible and intangible as it feels, is matter, and matter can be stored. The claim we have been building, that every breath mixes, that Caesar's exhalations are now everywhere, is no longer just arithmetic. It is chemistry. It is measurable fact, archived in ice, waiting for anyone with the patience and the tools to read it. But here the story gains a complication, because not every molecule exhaled remains in the air. The atmosphere is not a sealed jar. It is an open system, constantly exchanging matter with the ocean, the land, the living world. The planetary blender mixes, yes, but it also loses, and it gains. And the things it exchanges are not random. They are shaped by chemistry, by life, by the same forces that drive the carbon cycle and the water cycle and every other system that makes the Earth more than a dead rock orbiting a star. Consider what happens to carbon dioxide after you exhale it. It does not simply float, inert, waiting to be inhaled by someone else 2,000 years later. Some of it does. Nitrogen is stable. It does not react easily. It stays in the air for millions of years, cycling slowly through the soil when lightning or bacteria fix it into compounds plants can use. But mostly it just remains, a passive background. Carbon dioxide is different. It is reactive. It is in demand. Plants take it. Every green leaf on Earth is pulling carbon dioxide from the air, splitting it apart in the microscopic factories called chloroplasts, using the energy of sunlight to combine carbon with water and build sugars, glucose, sucrose, cellulose. The process is photosynthesis, and it happens on a scale difficult to comprehend. Global land plants taken together perform photosynthesis at a rate of 157 petagrams of carbon per year, 157 billion metric tons. That is carbon pulled from the atmosphere, locked into wood and roots and leaves and soil. Forests alone provide a net sink of 16 billion metric tons of carbon dioxide annually, even after accounting for deforestation and disturbance. The Amazon, the boreal forests of Canada and Russia, the savannas of Africa, every growing thing is an editor, removing carbon from circulation, at least temporarily. But plants do not hold carbon forever. They respire. At night, when photosynthesis stops, they burn sugars for energy and release carbon dioxide back into the air, just as animals do. They shed leaves, which decay. They die, and their tissues are broken down by fungi and bacteria, and the carbon returns. Fire accelerates the process. A wildfire converts organic matter into ash and smoke, releasing decades or centuries of accumulated carbon in a matter of hours. Some of the carbon becomes charcoal, black carbon, pyrogenic organic matter, which is more stable and can persist in soil for thousands of years. But most goes back into the air. The forest breathes out again. The ocean is an even larger editor. It absorbs roughly 30% of the carbon dioxide emitted by human activity, and it holds roughly 60 times more carbon than the atmosphere. Carbon dioxide dissolves in seawater, forming carbonic acid, which dissociates into bicarbonate and carbonate ions. The ocean's chemistry shifts, its pH drops. Since the pre-industrial era, global ocean acidity has increased by 40%. Coral reefs struggle. Shellfish find it harder to build their calcium carbonate shells, but the ocean keeps absorbing. It is patient, it is vast, and it is cold enough in the deep layers that the dissolved carbon can remain sequestered for centuries before it resurfaces in an upwelling current off the coast of Peru or Antarctica. Rain scavenges. Water vapor condenses on particles, dust, soot, pollen, salt, forming droplets that trap gases and carry them to the ground. Sulfur dioxide, nitrogen oxides, particulates, all washed out of the air with each storm. The process has two modes: in-cloud scavenging, where particles serve as the nuclei around which droplets form, and below-cloud washout, where falling rain collides with and captures airborne material. The result is the same. The air clears. The pollutants move into soil, into rivers, into the ocean. Rainforests are called the lungs of the earth, but rain itself is a kind of lung, inhaling the dirty air and exhaling it clean. Sunlight breaks bonds. High-energy ultraviolet photons split molecules apart in a process called photolysis. Nitrogen dioxide absorbs a photon and breaks into nitric oxide and a free oxygen atom. The oxygen atom collides with an oxygen molecule and forms ozone. Ozone itself is broken by ultraviolet light, releasing the oxygen again. The stratosphere is a battleground of photochemistry, reactions driven by light, cycling the same atoms through different configurations thousands of times before they drift back down to the surface. Some molecules are destroyed permanently, some are transformed. The atmosphere edits itself constantly, using the sun's energy as the knife. Microbes regulate the return. Soil bacteria decompose dead matter, breaking down cellulose and lignin, releasing carbon dioxide back into the air. After a wildfire, microbial biomass in the soil can drop by a third, but the ecosystem recovers. Fast-growing bacteria dominate the post-fire soil, and within 5 years the microbial community often returns to pre-burn levels. The carbon that was locked in wood becomes carbon in the air again, and the cycle continues. So the atmosphere is not a vault, it is a commons, a place where carbon passes through, briefly, on its way from one reservoir to another. The breath you exhaled 5 minutes ago still contains molecules that were in your lungs. But the breath you exhaled 5 years ago? Some of those molecules are in trees now. Some are dissolved in the Pacific. Some have been taken up by phytoplankton, consumed by krill, eaten by whales, and returned to the water as waste. Some have been rained out onto a wheat field in Kansas, absorbed by the soil, taken up by roots, built into grain, ground into flour, baked into bread, eaten by a child in Morocco, and exhaled again as part of that child's breath. The atmosphere does not hold everything. It passes things along. This complicates the elegant claim. If plants and oceans are constantly removing carbon dioxide, then the molecules Caesar exhaled, assuming they were carbon dioxide, which they were mixed with nitrogen and oxygen and water vapor, are no longer all in the air. Most of them are not. Most of them have been cycled through the biosphere 100 times or more. They have been part of trees and plankton and soil and whales and birds and bacteria and people. They have been in bread and bone and leaf and rain. They are still on Earth, still in the system, but they are not all in the air. Nitrogen, though. nitrogen stays. 78% of the atmosphere is nitrogen, and nitrogen does not leave easily. It is chemically lazy. It does not burn, does not dissolve readily in water, does not react with most things. Lightning can split the triple bond, combining nitrogen with oxygen to form nitrogen oxides that dissolve in rain and enter the soil. Certain bacteria can fix atmospheric nitrogen, converting it into ammonia that plants can use. But these processes are slow, and the nitrogen fixed each year is a tiny fraction of the atmospheric total. For practical purposes, the nitrogen Caesar exhaled is still there, still in the air, still circulating, still available to be inhaled by you, tonight, 2,000 years later. So the claim narrows, but it holds. Not every molecule from Caesar's breath is still airborne, but the nitrogen molecules are, and a single breath contains trillions of nitrogen molecules. The arithmetic still works, the diffusion still works, the mixing still works, and the result is the same. You are breathing nitrogen that passed through Caesar's lungs, through Cleopatra's, through the lungs of every human who lived long enough ago for the mixing to complete. The molecules are shared. They always have been. They always will be. Which brings us to carbon, the atom that moves. Trace a single carbon atom. Follow it as it leaves your mouth, part of a molecule of carbon dioxide exhaled into the room. It drifts. It mixes with the air. It rises on a thermal current and passes through an open window. It is carried by the wind across the city, over fields, across the continent. Within weeks it has crossed the ocean. Within months it is in the southern hemisphere. And then, one afternoon, it encounters a leaf. The leaf belongs to a wheat plant growing in a field in southern France. The carbon dioxide molecule, your molecule, diffuses through a tiny pore on the underside of the leaf called a stoma. Inside the leaf, in the cells of the mesophyll, it encounters a green organelle called a chloroplast. The chloroplast is packed with stacks of membranes embedded with chlorophyll, the molecule that captures light. A photon from the sun strikes the chlorophyll, excites an electron, and begins a cascade of reactions. Water molecules are split, releasing oxygen. The energy is used to combine carbon dioxide with a 5-carbon sugar, and the result is a 6-carbon molecule that is immediately broken into 2 3-carbon molecules. The cycle repeats. The 3-carbon molecules are converted into glucose. The glucose is linked into chains, forming starch, stored in the cells. The carbon atom, your carbon atom, is now part of the plant. The wheat grows, the grain ripens, the farmer harvests it. The grain is milled into flour. The flour is mixed with water and yeast and salt and baked into bread. A family in Lyon buys the loaf. A child takes a bite. The bread is chewed, swallowed, broken down by enzymes in the stomach and intestines. The glucose molecules are absorbed into the bloodstream, carried to the cells, transported into the mitochondria. There, in a process that mirrors photosynthesis in reverse, the glucose is combined with oxygen. The chemical bonds are broken. Energy is released. Carbon dioxide and water are the waste products. The carbon atom, the same atom you exhaled months ago, is exhaled again, by the child, into the air over Lyon, and the cycle begins again. This is not a metaphor. This is the fast carbon cycle, the movement of carbon between atmosphere, biosphere, and back again, turning over on timescales of years to decades. Every atom of carbon in your body right now was in the atmosphere recently. In the last year, the last 10 years, the last century. It was taken up by a plant, a grain, a vegetable, a fruit, or the grass eaten by a cow whose milk or meat you consumed. It was built into tissue, it was stored, and then it was released either by your respiration or by the respiration of the soil microbes that decomposed the plant after it died. The same atoms cycle endlessly. You are made of old air. Everyone is. Joseph Priestley figured part of this out in the summer of 1771. He was experimenting with air, trying to understand what happened to it when animals breathed or candles burned. He placed a sprig of mint in a sealed glass bell jar that had been spoiled by a burning candle and a mouse, air that could no longer support flame or life. He left the mint in sunlight for several days. When he returned, the air had been refreshed. A candle would burn in it again. A mouse could breathe it. The plant had somehow restored what the combustion and respiration had taken away. Priestley did not understand the mechanism, but he had discovered photosynthesis. He had demonstrated that plants and animals are not separate systems but linked parts of a cycle, exchanging gases, editing each other's air. 3 years later, on the 1st of August 1774, Priestley used a 12-inch burning lens to focus sunlight on a sample of mercuric oxide. A gas was released. He collected it, tested it, and found that a candle burned in it with a fierce, bright flame. He breathed some of it himself and noted that the feeling of it in my lungs was not sensibly different from that of common air, but I fancied that my breast felt peculiarly light and easy for some time afterwards. He called it dephlogisticated air. We call it oxygen. But Priestley never fully abandoned phlogiston theory, the old idea that combustion released a substance rather than consuming one. He was a brilliant experimenter, but his interpretations remained tangled in the framework he had inherited. Antoine Lavoisier, working in Paris, cut through the confusion. He identified oxygen, named it in 1778, and demonstrated that respiration is chemically identical to combustion. Both processes consume oxygen and produce carbon dioxide. Both release energy. The difference is only one of speed and control. A candle burns in seconds. A body burns over a lifetime, but the chemistry is the same. Lavoisier wrote it out precisely in his 1789 treatise, the Traité élémentaire de chimie, illustrated by his wife, Marie-Anne Pauls Lavoisier, who was also his collaborator and translator. The book dismantled the old chemistry and built the new one in its place. It is one of the foundational texts of modern science. Lavoisier did not live to see how far the implications would reach. On the 8th of May, 1794, he was executed by guillotine during the French Revolution. His plea for time to complete his experiments was rejected. A judge reportedly said, "The Republic has no need for scientists." His body was buried in an unmarked grave. His work was not. What Lavoisier proved is this. Breath is not separate from the world. It is part of the world's metabolism. You exhale carbon that was recently assembled in your cells. That carbon will be inhaled by someone else, or taken up by a plant, or dissolved into the ocean. It will cycle, and the carbon you inhale now was exhaled recently by someone else, or released by a forest, or lifted from the ocean surface by a wave. The atmosphere is not a storage vault, it is a relay. Every breath is both an inheritance and a gift, passed forward without ceremony, without awareness, without pause. Now go deeper, further back, before Caesar, before Rome, before the written record begins. The arithmetic does not stop at the edge of history. It continues backward through the long succession of human populations, through the migrations and settlements and extinctions, through the tens of thousands of years when our species lived without cities, without agriculture, without names that survived in any text. Every one of those people breathed. Every exhalation entered the same planetary system. The molecules dispersed, they mixed, and they are still here. Consider the early populations of Homo sapiens in Africa between 70,000 and 300,000 years ago. Small bands moving through savannas and river valleys, breathing the same nitrogen-rich air you breathe now. Their exhalations carried the same molecular signature: nitrogen, oxygen, carbon dioxide, water vapor, trace argon. The nitrogen, being chemically inert, remained in the atmosphere. It did not decay. It did not bond into soil or stone. It drifted north, east, across the emerging migratory routes. Some of it is in the room with you now. You cannot name them. No record survives. But the molecules do. Or go further. The Neanderthals, living across Eurasia from roughly 400,000 to 40,000 years ago. They breathed the same atmospheric reservoir. Their lungs processed the same oxygen, expelled the same waste gases. The carbon they exhaled has cycled many times since, through plants, through oceans, through the respiration of countless other organisms. But the nitrogen they exhaled, the stable diatomic molecules that make up the bulk of every breath, those did not transform. They entered the mix. They are part of the air now. This is not mythology. This is not ancestor worship. This is arithmetic and atmospheric physics applied to deep time. If Caesar's exhalation from 44 BCE statistically survives in a modern breath, then so do the exhalations of every human who lived long enough before him for their molecules to achieve global distribution. The mixing time is short, 1 to 2 years. The persistence time for nitrogen is effectively infinite on human timescales. The conclusion is unavoidable. Every breath you take contains molecular fragments of the long human past, from people whose names were never recorded, whose faces were never carved, whose lives left no trace except this one: exhaled air, mixed into the planetary atmosphere, waiting to be inhaled again. The numbers support this without sentiment. Earth's atmosphere contains roughly 10 to the 44th power molecules. A single human lifetime, assuming 70 years and an average respiratory rate, produces roughly 250 million breaths, each containing 25 sextillion molecules. Multiply that across the estimated 100 billion humans who have ever lived, and you arrive at a cumulative exhalation count on the order of 10 to the 19th total breaths, or roughly 10 to the 42nd molecules exhaled across all of human history. That is 1% of the atmosphere's total molecular inventory. One breath in every 100 molecules you inhale was, at some point, inside another human being. But the claim is stronger than that, because it is not asking whether your breath contains human molecules in general. It is asking whether it contains molecules from one specific person, and the answer depends on the size of the sample you're drawing. 25 sextillion molecules per breath. That is the number that collapses the improbable into the certain. Even if Caesar's molecules, or those of an anonymous ancestor from 50,000 years ago, represent only 1 part in 10 sextillion of the atmosphere, you're drawing 25 sextillion samples with every inhale. The odds that none of those samples came from a specific source become vanishingly small. Not zero, nothing in statistics is ever quite zero, but small enough that the reverse claim that you are not inhaling ancient air becomes the surprising one. Let that settle. Human history has always been materially entangled. The separation we assume between past and present, between the dead and the living, between one generation and the next, is a separation of time and information, not of matter. The matter cycles, it mixes, it does not care about chronology. A nitrogen molecule exhaled by a Neanderthal child 40,000 years ago in what is now France has had ample time to drift across continents, to be inhaled and exhaled by thousands of other organisms, to cross the equator a dozen times, to rise into the stratosphere and fall again, and to end up this morning in your lungs. You did not choose this, neither did they. It is simply the consequence of living on a planet with a mixed atmosphere and a finite molecular inventory. The air does not renew itself, it recycles, and because it recycles, it remembers, not in the sense of preserving information, but in the sense of preserving presence. The substance of the past remains present, not as a ghost, as a measurable statistical fact. Now test this against a harder case, not the general claim but the specific one. Julius Caesar died on the Ides of March 44 BCE in the Curia of Pompey, a meeting hall attached to the Theatre of Pompey in Rome. He was stabbed 23 times by a group of senators. His final breath, his actual terminal exhalation, left his lungs sometime in the moments after the attack, as his body shut down and his respiratory system ceased to function. That breath contained roughly 25 sextillion molecules. Most of it was nitrogen, some of it was oxygen, though he had consumed much of that. A small portion was carbon dioxide, the waste product of his cells. A trace was water vapour, argon, and the miscellaneous gases that comprise the last fraction of a percent of any exhalation. Where did those molecules go? They dispersed. Diffusion carried them outward from his body into the surrounding air of the Curia. Convection, driven by the temperature difference between his warm exhalation and the cooler air of the stone hall, carried them upward. Over the following hours and days they mixed with the air of Rome, drifting through the Forum, across the Tiber, into the hills and fields beyond. Wind carried them farther. The prevailing westerlies over the Mediterranean pushed them east. Some rose into the upper troposphere, caught in the Hadley circulation, and began the slow planetary loop that distributes air between hemispheres. Within a year, a significant fraction of those molecules had spread across Europe, North Africa, and the Near East. Within 2 years, they had mixed globally. That is the easy part. The dispersal is well understood. Now the harder question, are those molecules still airborne? Some are. The nitrogen molecules, which make up the majority of any breath, are chemically stable. They do not react readily with other substances. They do not dissolve into the ocean at high rates. They do not get locked into soil or stone on short timescales. They remain in the atmosphere for thousands, even millions of years. If Caesar's final exhalation contained roughly 20 sextillion nitrogen molecules, a reasonable estimate given that nitrogen comprises 78% of any breath, then most of those molecules are still in the atmosphere today, 2069 years later. Not all. Some have been removed by slow processes. lightning fixes a tiny fraction of atmospheric nitrogen into nitrates, which rain into soil and water. Some nitrogen is taken up by bacteria capable of nitrogen fixation, converted into organic compounds, and cycled through the biosphere. But these processes are slow, and the residence time for nitrogen in the atmosphere is long. The fraction of Caesar's nitrogen that has been permanently sequestered is small. Most of it is still aloft. The oxygen is gone. Oxygen is reactive. It is consumed by respiration, by combustion, by oxidation of metals and minerals. The oxygen molecules Caesar exhaled in 44 BCE have long since bonded with carbon to form carbon dioxide, or with hydrogen to form water, or with iron to form rust. They are no longer molecular oxygen, but the oxygen atoms persist, cycling through the biosphere, locked temporarily in organic matter, or dissolved in the ocean or bound in CO2, and eventually released again. The atoms remain. The molecules do not. The carbon dioxide he exhaled has also cycled. Most of it was absorbed by the ocean within a year. Some was taken up by plants and incorporated into wood, leaves, seeds. Some of that organic carbon was consumed by animals, respired again, and released back into the atmosphere. Some was buried in sediment and locked into rock over geological time. The carbon atoms from Caesar's breath are still on Earth, but they are no longer in the atmosphere in their original molecular form. They have been disassembled, rearranged, re-emitted, and disassembled again. The carbon has cycled dozens, perhaps hundreds of times since 44 BCE. So when we say you are breathing Caesar's air, what we mean precisely is this. You're inhaling nitrogen molecules that were present in his final exhalation, molecules that have remained chemically intact and globally distributed over 2 millennia. You're also inhaling oxygen atoms that were once part of the O2 or CO2 he exhaled, but those atoms have since bonded into different molecules, water, carbon dioxide, carbohydrates, proteins, and have been re-released into the atmosphere in new forms. The atoms persist. The original molecules, except for nitrogen, do not. This is not a failure of the claim. This is the claim, stated precisely. The statistical argument depends on large numbers and long time scales. Start with the ratio. Caesar's final breath contained 25 sextillion molecules. The atmosphere contains 10 to the 44th molecules. The ratio is 1 in 400 sextillion, or 1 in 4 times 10 to the 21st power. That is the fraction of the atmosphere represented by a single breath. Now ask, what is the probability that a breath you take today contains at least one molecule from that specific exhalation? The mathematics is straightforward. If the molecules have mixed uniformly, then each molecule in your breath has a 1 in 400 sextillion chance of being a Caesar molecule. You're drawing 25 sextillion samples. The probability that none of those samples is a Caesar molecule is the probability that you miss on the first draw, times the probability you miss on the second, times the probability you miss on the third, repeated 25 sextillion times. That probability is effectively zero. Run the numbers the other way. The probability that at least one molecule in your breath came from Caesar is, for practical purposes, 100%. Not certainty, statisticians do not deal in certainties, but close enough that the error is unmeasurable, and this holds for every breath, not just yours. Every breath taken by every person alive today, and every person who will live tomorrow, and every person who has lived since roughly 42 BCE, once sufficient mixing time had elapsed. The calculation is the same for Cleopatra, who died in 30 BCE, the same for Confucius, who died in 479 BCE, though the mixing time stretches longer and the probability approaches unity more slowly. The same for every human who lived long enough ago that their exhalations have had time to disperse globally and mix uniformly into the atmospheric reservoir. Go back 10,000 years, 20,000, 50,000. The principle does not change. The only variable is the number of molecules each person contributed and the time available for mixing. And because the atmosphere is old, billions of years old, and because nitrogen is stable on timescales far longer than human history, the conclusion stands. Every breath you take contains atoms exhaled by people who lived long before cities, before agriculture, before language as we would recognize it. This is the breath of the dead, not as poetry, as probability. But notice what the argument does not claim. It does not claim you can identify which molecules came from which person. You cannot. The mixing is too thorough. The molecules are indistinguishable. A nitrogen molecule is a nitrogen molecule. It carries no tag, no history, no information about where it has been or what lungs it has passed through. The claim is statistical, not forensic. It says that if you could somehow label every molecule Caesar exhaled, and if you could track them forward through 2,000 years of atmospheric mixing, you would find a few hundred of them, on average, in any given breath taken today. But you cannot label them. You cannot track them. You can only calculate the probability that they are there. And the probability is overwhelming. The uncertainty is not a weakness. It is the nature of statistical reasoning applied to systems this large. You cannot follow one molecule. You can follow the aggregate. And the aggregate behavior, over large samples and long times, is predictable. The air mixes, the molecules disperse, the ratios hold, and the conclusion follows. This is why the claim feels strange even after you understand the arithmetic. You're inhaling actual physical molecules that were inside other people. Not copies, not symbolic representations. The same nitrogen molecules. They left one set of lungs, drifted through 2,000 years of atmospheric circulation, and entered yours. The connection is material, direct, and unavoidable. Human history has always been materially entangled, whether anyone knew it or not. The air you breathe now was breathed before, many times, by people you will never know and whose names have been lost. It will be breathed again, long after you're gone, by people who will not know your name either. The atmosphere is a commons, a shared resource that does not recognize borders or centuries. It mixes everyone's exhalations into a single, planet-wide reservoir, and it distributes that mixture without preference or memory. You are part of that system. You always have been. Every breath you have ever taken contains fragments of the human past. Every breath you exhale becomes part of the human future. The separation is temporal, not material. The matter moves, it cycles, it connects, and there is no way to opt out. A signal. Everyone inhales. The same atmosphere that connects you to Caesar connects you to everyone alive right now. The mixing is not a relic of deep time alone. It is continuous, ongoing, happening at every moment. What goes into the air in one place does not stay there. It spreads, and that spreading has made the modern atmosphere legible in ways the ancient atmosphere never was. You cannot see Caesar's molecules, but you can see the signature of industrial civilization, written in the chemical composition of the air, measured with precision, updated every hour, plotted on a graph that has become one of the most important datasets in the history of environmental science. The place where that measurement began is remote, deliberate, chosen for its isolation. Mauna Loa Observatory sits more than 3,000 meters above sea level on the northern flank of a Hawaiian volcano, far from cities, far from forests, far from the localized distortions that come with human density or seasonal vegetation. The air that reaches the observatory has traveled across the Pacific, mixing as it moves, carrying with it not the breath of one person, but the aggregate exhalation of the whole world. It is about as close as you can get to a global average, sampled in real time. Charles David Keeling arrived there in 1958. He was a geochemist, trained at Northwestern and Caltech, methodical in temperament, convinced that the atmosphere could be measured accurately if the instruments were precise enough and the location carefully selected. He had spent the previous few years developing techniques for measuring carbon dioxide concentrations in air samples, refining the equipment, eliminating sources of error. When he set up his apparatus at Mauna Loa in March of that year, the idea was to take a snapshot, a baseline reading of atmospheric CO2 that could serve as a reference for future studies. What he did not expect was that the readings would continue, month after month, year after year, producing not a single data point but a continuous record, unbroken, stretching across decades. The graph that emerged from that record is now known as the Keeling curve. It is a simple thing to look at. Time on the horizontal axis, carbon dioxide concentration on the vertical, measured in parts per million. The line rises. It wiggles as it rises, small oscillations, regular, annual, corresponding to the seasonal cycle of plant growth and decay in the northern hemisphere, where most of the world's landmass sits. In the spring and summer, plants photosynthesize, pulling CO2 out of the air. The concentration drops. In the fall and winter, plants die back, decompose, release carbon. The concentration climbs. This is the breathing of the biosphere, visible at planetary scale, a rhythm that repeats every 12 months. But beneath the oscillations, the trend is unambiguous. The baseline rises. In 1958, Atmospheric CO2 stood at roughly 315 parts per million. By 1980, it had reached 338. By 2000, 369. By 2020, 412. By early 2026, it had crossed 432 parts per million. The rate of increase is not linear, it is accelerating. The steepness of the curve grows with each passing decade. The wiggle remains, the biosphere still breathes, but the long-term trajectory is upward, relentless, uninterrupted by recession or policy or awareness. This is the first time in human history that a single graph, derived from one instrument in one location, has captured a global transformation in progress. The atmosphere mixes. What Keeling measured at Mauna Loa was not the air above Hawaii. It was the air above everywhere, averaged and homogenized by the same circulation patterns that carry Caesar's molecules into your lungs. The CO2 rising in the Keeling curve is the sum of all the carbon dioxide added to the atmosphere by human activity. Fossil fuel combustion, deforestation, cement production, land use change, integrated over time, distributed globally, measured continuously. For 10,000 years before the mid-18th century, atmospheric CO2 concentrations held steady at around 280 parts per million. This stability shows up in ice cores, in trapped air bubbles, in the Vostok and Epica records discussed earlier. The number did not drift. It oscillated slightly year to year, but the average remained fixed, locked in a balance between sources and sinks, volcanoes and respiration adding carbon, oceans and photosynthesis removing it. Then the balance broke. Coal began to burn in large quantities. Oil wells opened. Internal combustion engines spread. Factories multiplied. And the concentration began to rise. The rise is not debated. The measurements are public, reproducible, cross-validated by networks of instruments around the world. What Keeling proved is that the increase is real, that it is sustained, and that it is accelerating. But the graph alone does not tell you where the carbon is coming from. It only tells you that it is accumulating. To know the source, you need a different kind of measurement. You need to look at the isotopes. Carbon comes in 3 naturally occurring isotopes. Carbon-12 is the most common, making up about 99% of all carbon on Earth. Carbon-13 is heavier, rarer, stable, comprising roughly 1%. Carbon-14 is radioactive, produced in the upper atmosphere by cosmic rays, decaying with a half-life of about 5,700 years. Living organisms incorporate all 3 isotopes in proportions that reflect the atmosphere they grow in. When a plant photosynthesizes, it takes in CO2, and that CO2 carries the isotopic signature of the air at that moment. When the plant dies and gets buried and, over millions of years, turns into coal or oil or natural gas, the carbon it contains is still isotopically labeled, a chemical record of the atmosphere that existed when the plant was alive. Here is the key point. Fossil fuels are old, millions of years old. The carbon-14 they once contained has long since decayed. It is gone. And the ratio of carbon-13 to carbon-12 in fossil carbon is lower than the ratio in the modern atmosphere, because ancient plants preferentially incorporated the lighter isotope during photosynthesis. So when you burn fossil fuels and release their carbon into the air, you are adding CO2 that is depleted in both carbon-13 and carbon-14 relative to the background. You're changing the isotopic signature of the atmosphere in a way that is measurable, specific, and diagnostic. This is called the Suess effect, named after the Austrian chemist Hans Suess, who documented the dilution of carbon-14 in the atmosphere in the 1950s as fossil fuel combustion increased. The effect is unmistakable. As CO2 concentrations have risen, the fraction of carbon-14 in atmospheric CO2 has fallen, and the ratio of carbon-13 to carbon-12 has shifted downward. Both changes point to the same source: fossil carbon, sequestered underground for millions of years, now being released into the atmosphere faster than natural processes can absorb it. The isotopic evidence does not rely on models. It does not depend on assumptions about climate sensitivity or feedback loops. It is direct chemical fingerprinting. The carbon accumulating in the atmosphere is ancient, and it came from burning coal, oil, and gas. The same mixing that connects people across centuries now distributes the chemical consequence of industrial activity around the planet. The CO2 you exhale is local, temporary, part of the short-term carbon cycle. It came from food, which came from plants, which pulled it out of the air months or years ago. That carbon returns to the atmosphere quickly, and it is reabsorbed quickly. It cycles. But the CO2 released by burning fossil fuels is different. It is not part of the active cycle. It is a one-way addition, a transfer from the geological reservoir into the atmospheric one. And because the atmosphere mixes globally, that addition becomes everyone's problem, everywhere, all at once. By 2015, the American Chemical Society designated the Mauna Loa CO2 record a National Historic Chemical Landmark, recognizing it as evidence that linked fossil fuel combustion to observable, measurable changes in the global atmosphere. When Keeling died in 2005, his son Ralph took over the program at the Scripps Institution of Oceanography, ensuring the continuity of the dataset. The record continues, the line rises, the curve does not flatten, and every breath you take now contains not just the nitrogen molecules of the distant dead, but a trace of carbon dioxide added by the collective activity of the present, a signal everyone inhales, whether they live near a coal plant or in the middle of the Pacific, whether they burn fossil fuels themselves or have never touched a drop of gasoline. The atmosphere does not distinguish. It mixes, it averages, it distributes. The same physics that made Caesar's breath everyone's breath has made industrial emissions everyone's air. When shared air becomes threat, the wonder of atmospheric connection does not arrive alone. It comes with consequence. The same mixing that distributes molecules evenly over time also distributes harm. And harm, unlike stable nitrogen, does not wait for years to circulate. It moves faster, it concentrates locally, it follows the wind. In the summer of 2023, Canada experienced the most intense wildfire season in its recorded history. More than 6,000 fires burned across the country between March and November, consuming 18.5 million hectares, an area roughly the size of Syria. The smoke from those fires did not stay in Canada. It travelled. Prevailing winds carried it south and east, across the border, into the densely populated corridor of the eastern United States. From late May through early July, cities that had not seen wildfire smoke in living memory, New York, Philadelphia, Washington, were blanketed under thick orange haze. Air quality indices, which measure the concentration of fine particulate matter in the atmosphere, spiked into hazardous ranges. Residents were advised to stay indoors, to close windows, to avoid exertion. The sky turned the colour of a dimming lamp. The sun, when visible, appeared as a pale red disk, its light scattered and absorbed by particles too small to see, but large enough to lodge deep in the lungs. This was not the first time wildfire smoke had crossed long distances. It was simply the most visible, the most sustained, and the most widely experienced by populations unaccustomed to it. The smoke contained fine particulate matter, PM2.5, defined as particles 2.5 micrometers in diameter or smaller. These particles are produced by incomplete combustion. They consist of soot, ash, organic compounds, and trace metals suspended in air, light enough to stay aloft for days or weeks, small enough to bypass the body's defenses. When inhaled, they penetrate deep into the respiratory system, reaching the alveoli, crossing into the bloodstream. They are linked to cardiovascular disease, respiratory illness, stroke, and premature death. Studies estimate that wildfire smoke alone is responsible for roughly 40,000 premature deaths annually in the United States, a number that has been rising as fire seasons lengthen and intensify. The atmosphere connects. That connection is not neutral. It does not only carry nitrogen and oxygen and the inert remnants of ancient exhalations, it carries whatever is put into it, and what is put into it increasingly includes things the body was not designed to handle. Consider another example. Every summer, dust from the Sahara Desert is lifted into the atmosphere by strong winds, carried westward across the Atlantic Ocean, and deposited across the Caribbean and the southern United States. This is not a new phenomenon. It has been happening for millennia. The dust is rich in minerals, iron, phosphorus, and it nourishes marine ecosystems and rainforests on the other side of the ocean. But it also carries risks. Saharan dust increases concentrations of PM10 and PM2.5 in the air, triggering spikes in emergency room visits for asthma, particularly among children. The dust plumes are largest between mid-June and mid-August, coinciding with the Atlantic hurricane season, and their arrival is predictable, trackable, mapped by satellite. The same is true of pollution transported across national borders. A 2007 study calculated that approximately 12% of global premature deaths related to fine particulate matter more than 400,000 deaths, were caused by pollutants that originated in one country and were carried by atmospheric circulation into another. Coal plants in one nation send sulfur dioxide and nitrogen oxides into the jet stream, where they travel hundreds or thousands of kilometers before being deposited as acid rain or inhaled as aerosols. The atmosphere does not respect borders. It does not enforce sovereignty. It mixes and it moves, and it delivers the consequences of one population's activity to another, often to populations that contributed little to the emissions and have limited capacity to respond. Here is where the central fact of this documentary gains moral force. Atmospheric connectedness is real. It is measurable. It is unavoidable, but it is not evenly experienced. The same air that connects everyone does not affect everyone equally. Exposure depends on geography, on proximity to sources, on the built environment, on economic access to filtration and medical care. A 2022 study published in Nature found that racial and ethnic minorities and low-income populations in the United States are consistently exposed to higher levels of fine particulate pollution than wealthier, predominantly white communities, even when controlling for urbanization and industrial activity. The disparities are not accidental. They are structural, the result of zoning decisions, highway placements, the location of power plants and waste facilities, the availability of green space and ventilation. The atmosphere mixes over time, but time is the variable. In the near field, minutes, hours, days, the air does not average, it concentrates. The person downwind of a smokestack breathes different air than the person upwind. The child living next to a highway inhales more particulate matter than the child in a suburban cul-de-sac. The resident of a poorly ventilated apartment building is exposed to higher concentrations of indoor pollutants than someone in a house with mechanical ventilation and air filtration. The mixing happens eventually, but eventually is not now, and now is where the harm occurs. The arithmetic that makes Caesar's molecules statistically present in every breath assumes thorough mixing and sufficient time. It is a long-term average, a planetary equilibrium. But most air pollution operates on a different timescale. It is local first, regional second, global only after weeks or months of dispersion. The harm is front-loaded, the exposure is unequal, and the populations least responsible for the emissions are often the ones who bear the burden first and hardest. This is the turning point in the narrative. The wonder of shared air does not erase the reality of shared harm. The two facts coexist and they are connected. The atmosphere is a commons, and a commons can be degraded. It can be filled with things that hurt, and because it mixes, because it does not stay still, the degradation spreads, slowly, unevenly, but inevitably. What goes into the air in one place becomes part of the air everywhere, given time. The responsibility is collective, whether the choices were collective or not. The room we make together. Then came a moment when the invisible became urgent, when the abstraction of atmospheric mixing turned into a matter of immediate personal risk, when the breath of strangers was no longer a poetic connection across centuries but a transmission vector operating over minutes and meters. The COVID-19 pandemic made exhalation a public fact, and it forced a reckoning with the air inside enclosed spaces, the rooms we share, the buildings we occupy, the ventilation systems we take for granted or ignore. On the evening of March 10, 2020, 61 members of the Skagit Valley Chorale gathered for rehearsal at the Mount Vernon Presbyterian Church in Mount Vernon, Washington. It was a regular event, held weekly, a routine part of the choir's schedule. The rehearsal lasted 2.5 hours. The singers stood in rows, as choirs do, facing forward, breathing deeply, projecting their voices into the room. No one knew at the time that one person in attendance was infected with SARS-CoV-2, the virus that causes COVID-19. No one showed symptoms. There was no reason to suspect exposure. The room was large, the ceiling high, the doors were closed. Within days, people began to fall ill. Fever, cough, fatigue, shortness of breath. By the end of the month, 53 of the 61 attendees, 87%, had contracted COVID-19. 32 cases were confirmed by PCR testing. 20 were classified as probable, based on symptoms and epidemiological links. 3 people were hospitalized. 2 died. The outbreak became one of the most scrutinized transmission events of the early pandemic. Public health officials investigated. Researchers modeled the aerosol dynamics. The conclusion was unavoidable. The virus had spread through the air, not through surfaces, not through large respiratory droplets that fall quickly to the ground. Through aerosols, tiny particles smaller than 5 micrometers, generated by breathing and speaking, and especially by singing. These particles are light enough to remain suspended in the air for extended periods. They drift, they accumulate. In a poorly ventilated room, they build up over time, increasing the concentration of infectious material in the shared air. Every person in the room was inhaling what every other person was exhaling. The air was common, the exposure was common, and the virus moved accordingly. This was not how most people thought about disease transmission. The prevailing model, inherited from decades of public health guidance, focused on close contact, droplet spray, contaminated surfaces, 6 feet of distance, wash your hands, wipe down countertops. Those measures mattered, but they did not address the primary route the virus was travelling. The air itself was the medium, and the air in an enclosed space without adequate ventilation does not refresh quickly. It lingers, it recirculates. What one person exhales, another inhales. The recognition of airborne transmission did not come easily. It required advocacy, evidence, persistence. One of the most prominent voices pushing for that recognition was Lydia Morawska, a distinguished professor and director of the International Laboratory for Air Quality and Health at the Queensland University of Technology in Australia. Morawska had spent decades studying aerosols, how they form, how they behave, how they transport pollutants and pathogens. In the early months of the pandemic, she co-authored an open letter, published in July 2020 in the journal Clinical Infectious Diseases, titled "It is Time to Address Airborne Transmission of Coronavirus Disease 2019. The letter was signed by more than 200 scientists from around the world. It called on the World Health Organization and other public health agencies to acknowledge that SARS-CoV-2 could spread through the air, not just through droplets, and to update guidance accordingly. The argument was straightforward. Outbreaks like the one in Skagit Valley could not be explained by droplet transmission alone. The distances were too great, the surface contact too limited, the ventilation too poor. The only mechanism that fit the observed pattern was aerosol transmission, virus-laden particles suspended in the air, inhaled by people across the room, building up in concentration over time. The physics was well understood. The evidence was mounting. What was needed was recognition and action. Eventually, the guidance changed. Masks became ubiquitous. Ventilation became a priority. HEPA filters appeared in schools and offices. Windows that had been sealed shut for decades were opened. The infrastructure of indoor air, long neglected, became a matter of survival. And the lesson, though learned slowly and unevenly, was clear. The air in a room is shared. What you exhale, others inhale. The separation is not spatial. It is temporal, and the time is short. The same mixing that operates on the scale of the planet, dispersing molecules across continents, across centuries, operates on the scale of a room. Faster, yes. More concentrated, yes. But the principle is identical. Air is a fluid. It moves. It carries whatever is in it. And in an enclosed space, the mixing happens quickly enough that everyone inside is breathing a common atmosphere, an aggregate of all the exhalations in the room, blended and recirculated by convection and ventilation, or, in the absence of ventilation, by convection alone. The Skagit Valley Corral outbreak was not unique. Similar clusters appeared in restaurants, in gyms, in buses, in offices, in nursing homes. Each one reinforced the same conclusion. Indoor air is a shared resource, and it can become a shared risk. The concentration of infectious particles depends on ventilation, how much fresh air is brought in, how quickly the stale air is removed. In a well-ventilated room, the air turns over frequently. Particles are diluted, dispersed, exhausted to the outside. In a poorly ventilated room, they accumulate. The risk grows with time. This is where the physics of breath becomes a matter of responsibility. You cannot see the aerosols. You cannot feel them. But they are there, suspended, drifting, inhaled. The act of breathing, which has been presented in this documentary as a connection to the past, is also a connection to the present, immediate and inescapable. The room you're in right now has an atmosphere, and that atmosphere is made up of contributions from everyone who is in the room with you, and everyone who was in the room before you, depending on how recently the air was refreshed. You are breathing what they exhaled. They are breathing what you exhale. The air does not belong to anyone. It is common, and it makes you responsible to each other whether you acknowledge that responsibility or not. There is a further implication. Some people, for reasons not entirely understood, release far more aerosol particles when they breathe or speak than others. These individuals have been called super-emitters. They are not doing anything different. They are simply exhaling at a higher rate of particle generation, possibly due to the hydration of their respiratory tract, the structure of their vocal cords, the force of their exhalation. A super-emitter in a room can dominate the aerosol concentration, contributing a disproportionate share of the infectious load. This introduces randomness into transmission. Two gatherings, seemingly identical, can have wildly different outcomes depending on who is present, where they are positioned, how long they stay, how much they speak or sing. The Skagit Valley Chorale was founded in 1984. It was led by Dr. Yvette Burdick, an experienced choral director. The group was close-knit, committed, skilled. The rehearsal on March 10th was routine. Nothing about it was reckless. The members followed the guidance available at the time. They did not know that guidance was incomplete. They could not have known, and yet the outcome was devastating. The outbreak became a case study, cited in papers, analysed in models, used to justify changes in public health policy around the world. A local tragedy became a turning point in global understanding. The air you breathe is not private. It never has been. The molecules connect you to the past. The aerosols connect you to the present. The breath that connects you to Julius Caesar also connects you to the stranger beside you on the bus, to the child in the next room, to the co-worker across the table. That is the double edge of the arithmetic. It is beautiful when it reaches backward across centuries. It is urgent when it reaches sideways across a room. Now at last we must turn the arithmetic around and hold it up to the hardest light. The arithmetic that will not go away. The claim has been stated many times now, in many forms. Every breath you take contains atoms exhaled by anyone who ever lived. It is the thesis of this documentary. It is the reason you are still listening, or still drifting. It is the strangest true thing about being alive. But now we must ask, is it true? Not true in the sense of beautiful, not true in the sense of compelling, true in the sense that if you stopped a physicist in the hallway and made them check the math, they would nod and say yes, that holds. The answer is yes. But the path to yes is more interesting than the slogan, and it requires that we separate what is exact from what is approximate, what is certain from what is probable, and what the claim actually means from what it seems to mean. Start with the number everyone remembers. One breath contains roughly 25 sextillion molecules. That number has appeared again and again in this documentary. It is shorthand for the molecular abundance in half a litre of air, the volume of a typical inhalation. The figure is not guessed. It is derived from Avogadro's constant, from the ideal gas law, from measurements of temperature and pressure that have been refined over centuries. At sea level, at 15 degrees Celsius, half a litre of air contains approximately 1.3 times 10 to the 22nd molecules, 13 billion trillion. The number is almost incomprehensibly large, but it is not uncertain. It is a consequence of the scale at which matter is built. The atmosphere in turn contains roughly 10 to the 44th molecules. That number is equally solid. The atmosphere has been weighed. Its total mass is approximately 5.15 times 10 to the 18th kilograms. Most of that mass is nitrogen and oxygen. The rest is argon, carbon dioxide, water vapor, trace gases, particulates. The molecular count follows from the mass and the average molecular weight of air, which is known. These are not estimates, they are measurements. The ratio is what creates the claim. One breath is roughly 1 part in 800 sextillion of the total atmosphere. That ratio is so small that it feels like a guarantee of separation. If you exhale a breath, and that breath disperses into the atmosphere, the odds that any specific molecule from that breath will end up in any specific future breath seem impossibly remote. And they are remote. For any single molecule, the odds are 1 in 800 sextillion. But you did not exhale one molecule, you exhaled 25 sextillion molecules, and that changes everything. This is the structure of the lottery we have been discussing. The odds per ticket are terrible, but the number of tickets is so large that winning becomes not just possible, but probable. If Julius Caesar exhaled 25 sextillion molecules in his final breath, and those molecules mixed uniformly throughout the atmosphere, then any breath you take today, assuming perfect mixing and no removal, will contain, on average, several hundred molecules from that exhalation. The calculation is simple division. 25 sextillion divided by 800 sextillion equals roughly 3/100ths. Multiply by the size of your breath, and you get about 400 molecules. The number varies depending on whose figures you use for lung capacity and atmospheric volume, but it always lands in the hundreds. It is not a fringe outcome, it is the expected value. That is the claim. And that is where the interrogation begins. First question, is the atmosphere actually well mixed? The answer, over sufficient time, is yes. The previous section discussed the Keeling curve, which measures carbon dioxide concentrations at Mauna Loa. The curve shows seasonal oscillations, a sawtooth pattern reflecting the northern hemisphere's growing season, but those oscillations sit on top of a globally coherent trend. Carbon dioxide released in Beijing shows up in Hawaii, in Antarctica, in Buenos Aires, within 1 to 2 years. The atmosphere does not have walls, it does not have compartments, gases diffuse, winds blow, convection cells turn over. The troposphere, where most of the air resides, mixes thoroughly on a timescale of months to years. Stratospheric air mixes more slowly, but it too eventually circulates. The atmosphere is not perfectly uniform at any instant. There are gradients, pockets, local variations, but over years and decades the mixing is real. A molecule released at ground level in Rome in 44 BCE has had 2,000 years to wander. It has crossed every latitude, every longitude, every altitude accessible to the troposphere. It has been part of high-pressure systems and low-pressure troughs, part of monsoons and doldrums and trade winds. It has circled the Earth hundreds of times. The mixing assumption is not wishful thinking, it is atmospheric physics. Second question, do the molecules persist, or are they destroyed? This is where the claim requires precision. The slogan says molecules, but molecules are not indestructible. A molecule of carbon dioxide exhaled by Caesar does not remain carbon dioxide. Plants absorb it during photosynthesis. Oceans dissolve it. The carbon atom is stripped away, incorporated into a sugar, burned for energy, exhaled again by another organism, absorbed again, cycled again. The carbon persists, but the molecule does not. The same is true for water vapor, which condenses into clouds, falls as rain, evaporates, recondenses. The water molecule is constantly being assembled and disassembled. Even oxygen molecules, which are more stable, do not last indefinitely. They are consumed in respiration, in combustion, in oxidation. They are broken apart, bonded to carbon, to hydrogen, to iron. The oxygen atoms endure, but the molecules turn over. Nitrogen is different. Nitrogen makes up 78% of the atmosphere, and nitrogen molecules are extraordinarily stable. The triple bond between two nitrogen atoms is one of the strongest bonds in chemistry. Nitrogen does not react easily. It does not dissolve readily in water. It does not photolyze in sunlight. It does not get absorbed by most biological systems in its molecular form. Plants cannot use nitrogen gas directly. They require it to be fixed, converted to ammonia or nitrate, by specialized bacteria or by lightning. Animals acquire nitrogen through their diet, not through breathing. The nitrogen you inhale is the nitrogen you exhale, chemically unchanged. It passes through your lungs as a bystander, an inert cushion around the oxygen you need and the carbon dioxide you discard. This is the molecule that carries the claim. When the documentary says you are breathing molecules exhaled by Caesar, it is primarily referring to nitrogen molecules. Those molecules do persist. They have been in the atmosphere for millions of years. They were there before humans evolved. They will be there after we are gone. They are the stable background against which the rest of the chemistry happens. And because they persist, because they mix, and because there are so many of them in every breath the arithmetic holds, you are inhaling nitrogen molecules that pass through Caesar's lungs. Not all of them, not even most of them, but hundreds of them, in every breath, statistically speaking. Third question, does anyone who ever lived really mean everyone? This is where the claim must be qualified. The slogan is broad. Anyone who ever lived. It sounds like it includes every human being who has ever drawn breath, from the earliest Homo sapiens in Africa 300,000 years ago to the person who died this morning. But the arithmetic does not treat all individuals equally. Start with recent deaths. If someone died this morning, their final exhalation has not had time to mix globally. The molecules are still local, still concentrated near the place of death. If you are on the other side of the planet, you will not encounter those molecules for months or years. The mixing takes time. so the claim applies most strongly to individuals who died long enough ago that their exhalations have fully dispersed. How long is long enough? For tropospheric mixing, 1 to 2 years is sufficient. For stratospheric mixing, longer. The cutoff is not sharp, but as a rough guideline, anyone who died more than a few years ago has contributed to the global atmospheric reservoir. Anyone who died more recently has contributed locally. Now go backward in time. Julius Caesar died in 44 BCE. His molecules have mixed for over 2,000 years. The claim is solid. But what about earlier populations, Neanderthals, who went extinct approximately 40,000 years ago? Early Homo sapiens, who lived 100,000, 200,000, 300,000 years ago, do their molecules persist? The answer is mostly yes, but with a caveat. Nitrogen molecules are stable, but the atmosphere is not a closed system. Nitrogen is slowly lost to space, stripped away by solar wind at the top of the atmosphere, and slowly replenished by volcanic outgassing and biological nitrogen fixation. The residence time of a nitrogen molecule in the atmosphere is on the order of millions of years. Over the span of human history, the turnover is negligible. The nitrogen exhaled by a Neanderthal in what is now France 40,000 years ago is still in the atmosphere. It has not decayed, it has not been buried, it is still circulating. The same is true for early Homo sapiens. Their nitrogen molecules are part of the atmospheric pool, but there is a demographic wrinkle. The total number of humans who have ever lived is uncertain, but estimates cluster around 60 to 100 billion individuals. The lower estimates come from conservative assumptions about ancient population sizes. The higher estimates come from more generous assumptions. The Population Reference Bureau, often cited, places the figure at roughly 117 billion. But other scholars argue for lower numbers, pointing out that early human populations were small, scattered, and lived short lives. A reasonable median estimate is perhaps 60 to 80 billion. The uncertainty matters, because the total number of breaths ever taken by all humans depends on how many humans there were and how long they lived. Each human being takes on average roughly 500 million breaths over a lifetime. If you live 70 years and you breathe 12 times per minute, that is about 600 million breaths. Multiply by the number of humans who have ever lived, and you get a staggering total. If 80 billion humans lived, each taking 500 million breaths, that is roughly 4 times 10 to the 19 total human breaths, cumulative, over the entire span of our species. 4 times 10 to the 19 breaths, each containing roughly 25 sextillion molecules, gives a total on the order of 10 to the 42 molecules exhaled by all humans in history. Compare that to the atmosphere's total of 10 to the 44th molecules. The ratio is 1 in 100. 1% of the atmosphere, by molecular count, consists of molecules that have passed through human lungs at some point in history. That is the collective human contribution. It is not large, but it is not negligible. 1% means that every breath you take, which contains 25 sextillion molecules, contains roughly 250 billion trillion molecules that were once inside another human being. That is the stronger version of the claim. Not just molecules from one specific person, Caesar, Cleopatra, Confucius, but molecules from the aggregate of all human respiration, hundreds of billions of them in every inhale. But now the distinction between molecules and atoms becomes critical. The nitrogen molecules persist, as argued. But what about the oxygen and carbon dioxide? Those molecules do not persist, they cycle. The oxygen you inhale was likely produced by photosynthesis within the last few decades. The carbon dioxide you exhale will be absorbed by a plant, possibly within the next season. The molecules are transient, but the atoms are not. Carbon atoms, oxygen atoms, they are conserved. They move through the biosphere, through the oceans, through the soil, through the atmosphere, but they do not disappear. They are rearranged but not destroyed. So if the claim is rephrased, every breath you take contains atoms that were once inside another human being, the answer is unambiguously yes. Not just from human respiration, but from the entire biosphere. The carbon in your body came from the food you ate, which came from plants or animals, which acquired their carbon from the atmosphere, which acquired it from decomposition, combustion, respiration, outgassing. That carbon has been cycled and recycled through countless organisms. The oxygen in the water you drink, in the air you breathe, has been part of rivers, oceans, clouds, ice, blood, sap. The atoms are ancient. They have been on Earth for billions of years. They have been inside bacteria, inside dinosaurs, inside trees, inside emperors and peasants, and everyone in between. The atomic claim is not probabilistic, it is certain. The molecular claim, specifically, that you are breathing intact nitrogen molecules from Caesar's lungs, is probabilistic. It is not certain for any given breath, but it is overwhelmingly likely over the course of a day. If you take 20,000 breaths per day, and each breath contains, on average, 400 nitrogen molecules from Caesar, then you are inhaling roughly 8 million molecules from Caesar per day. The probability that you go an entire day without encountering a single one is vanishingly small. It is not zero, but it is effectively zero. The same logic applies to every other historical figure who lived long enough ago for their exhalations to mix. Cleopatra, Confucius, Genghis Khan, Joan of Arc, Shakespeare, Leonardo, Harriet Tubman. Pick anyone who died more than a few years ago, and you are breathing molecules they exhaled. The number per breath is small, often just a few hundred, but the cumulative count over a lifetime is enormous. Fourth question: what about people whose bodies were buried, or burned, or lost at sea? This is a question about completeness. Did all of their exhalations reach the atmosphere, or were some lost to other reservoirs? The answer is that most exhalations reach the atmosphere immediately. When you exhale, the breath disperses into the air. It does not get trapped. It does not settle. It becomes part of the ambient atmosphere within seconds. So every breath a person took during their life contributed molecules to the atmospheric pool. The exception is the final breath, and even then the exception is partial. If someone dies and their body's buried quickly, the air in their lungs at the moment of death may not fully escape. Some of it may remain in the lungs, trapped, until decomposition releases it. But decomposition does release it. The body decays. Gases are produced: methane, hydrogen sulfide, carbon dioxide, nitrogen. The nitrogen that was in the lungs and the nitrogen that was dissolved in the tissues eventually returns to the atmosphere, either directly or via the soil. The timescale is longer, but the contribution is made. The same is true for cremation. Burning a body releases gases: water vapor, carbon dioxide, nitrogen oxides. The nitrogen in the tissues is oxidized, released, mixed. Nothing is permanently sequestered unless it is fossilized, and fossilization is rare. For the vast majority of humans who have ever lived, their atoms and molecules have returned to the atmosphere. They are part of the pool. Fifth question: does the claim work for populations that lived in geographic isolation? This is a question about mixing across spatial scales. If a group of humans lived on a remote island, or in a deep valley, or in a region with limited atmospheric exchange, do their molecules still reach the rest of the world? The answer is yes, but it takes longer. Local geography can slow mixing, but it cannot prevent it. The atmosphere is a fluid. It has no fixed boundaries within itself. Air moves from high pressure to low pressure. It moves in response to temperature gradients, to the rotation of the Earth, to the heating and cooling of land and sea. A molecule exhaled on an island in the Pacific will be carried by trade winds, by cyclones, by the general circulation of the atmosphere. It will cross the ocean. It will reach other continents. The time required depends on the distance and the circulation patterns, but over years and decades the molecule will mix globally. The Keeling curve is proof of this. Carbon dioxide released anywhere on Earth contributes to the global average. The same is true for nitrogen, for oxygen, for any long-lived atmospheric gas. Geographic isolation delays mixing. It does not prevent it. Sixth question: what about the slogan itself? Anyone who ever lived. The phrase is poetic. It is evocative. It is emotionally resonant. But it is not technically accurate if interpreted literally. The claim does not mean that you are guaranteed to breathe molecules from every single individual human who ever existed. It means that for any individual who died long enough ago for their exhalations to mix, and who lived long enough to exhale a significant number of breaths, you are statistically likely to encounter molecules from them over the course of your lifetime. The probability approaches certainty for famous individuals whose exhalations have been thoroughly mixed over centuries or millennia. It is lower for individuals who lived only briefly or who died very recently. But the cumulative claim that every breath contains molecules from a vast number of past lives is robust. You are not breathing molecules from every human. You're breathing molecules from many humans, hundreds of them, perhaps thousands, depending on how you count and how you define the threshold. The honest version of the claim then is this: Every breath you take contains nitrogen molecules that pass through the lungs of many humans who lived before you, and it contains atoms, carbon, oxygen, hydrogen, that have cycled through the bodies of countless organisms over the history of life on Earth. The molecular connection is probabilistic and applies most strongly to long-lived atmospheric gases like nitrogen. The atomic connection is certain and applies to all elements. The slogan simplifies this. It sacrifices precision for impact. But the underlying truth is stronger, not weaker, when the details are examined. The arithmetic will not go away. You can adjust the numbers, you can account for removal processes, for incomplete mixing, for the difference between molecules and atoms. You can narrow the claim to nitrogen, or broaden it to all atoms. You can restrict it to individuals who lived long ago or expand it to include recent populations still mixing. No matter how you refine the calculation, the conclusion remains. The air you breathe is not new, it is not private, it is a shared inheritance, material and measurable, linking you to the past in a way that is not metaphorical. The atoms in your lungs have been inside other lungs, they have been inside other bodies, they have been part of other lives. That is not mysticism. It is conservation of matter. It is the finite size of the Earth system. It is the fact that nothing leaves, and it is unavoidable. No private air. You are breathing right now. You did not choose to. You did not think about it. Your diaphragm contracted, your ribcage expanded, and half a litre of air flowed into your lungs. The air came from wherever you are. Your room, your car, your office, the street, the field, the forest. It came from a few centimetres away, drawn in by the pressure gradient your lungs created. It was not special air. It was not curated. It was simply the air that was there. That air is a mixture. It contains nitrogen exhaled by a woman in Jakarta 3 months ago. It contains oxygen produced by a forest in Siberia last summer. It contains carbon dioxide from a coal plant in Shaanxi, from a wildfire in British Columbia, from the respiration of soil bacteria in the Amazon. It contains argon that has been in the atmosphere for millions of years, water vapour that evaporated from the Indian Ocean last week, and a trace of methane released by a wetland in Botswana. It contains pollen, dust, microplastics, industrial pollutants, and molecules exhaled by Julius Caesar, by Cleopatra, by people whose names were never recorded, and whose lives left no trace except the breath they contributed to the common atmosphere. You did not ask for any of this, you did not consent to it, but you received it, because there is no other air to breathe. This is the final implication of the arithmetic. The atmosphere is common, it is a shared physical system, and participation is not optional. You cannot breathe selectively, you cannot filter the atmosphere by origin, you cannot refuse the molecules that drifted from a distant place or a distant time. The air enters your lungs as an aggregate, a blend, a statistical average of everything that has been emitted and mixed. You are part of that system, not as an observer, not as a visitor, but as a contributor and a recipient. What you exhale joins the mixture. What others exhale, you inhale. The boundary between your air and someone else's air does not exist. This is true on the scale of the planet. It is also true on the scale of the room. The previous section described the Skagit Valley Chorale, where 61 people gathered to sing, and 53 were infected because the air they shared carried a virus. The lesson of that outbreak was not that singing is dangerous, or that gatherings are dangerous, but that air is a medium. It carries what is put into it, and in an enclosed space the air is shared more immediately, more intimately than most people realize. The breath you just exhaled is, within minutes, distributed throughout the room. It is inhaled by the person next to you, by the person across the table, by the person standing near the door. Their exhalations reach you just as quickly. The air mixes. The particles disperse. The separation you feel is psychological, not physical. This is where the documentary's central claim shifts from the distant past to the immediate present. The same arithmetic that connects you to ancient Rome connects you to the person breathing beside you. The same mixing that disperses Caesar's molecules across millennia disperses your neighbour's molecules across meters. The same atmospheric physics that makes one claim true makes the other claim true. They are not separate phenomena. They are the same phenomenon, operating at different timescales and different spatial scales, but governed by the same fluid dynamics, the same diffusion, the same conservation of matter. And this makes the atmosphere not just a source of connection, but a source of responsibility. You cannot see what you exhale, you cannot see what others exhale, but it is there, suspended, drifting, carried by convection and by breath. If you are sick, you exhale pathogens. If you are healthy, you exhale carbon dioxide, water vapor, volatile organic compounds, aerosols. If you are standing near a fire, you carry smoke into the room. If you have been in a polluted area, you carry pollutants. The air around you is not neutral. It is a record of where you have